So you need to know more about properties of solutions. Well, you came to the right place. Properties of solutions is chapter 13. Before you continue, make sure you have a paper, a pencil, and a periodic table out in front of you. Periodic table like this will do fine. Any other kind of periodic table is okay. Got to be able to write down all of these notes, neat and large, so then you can learn some stuff about chapter 13, properties of solutions. When we're done with this part, we'll talk about the test, so make sure that you've got your multiple choice portion of your test and the Scantron sheet and some paper for corrections. Pause the video now, make sure you have these 5 things available. Chapter 13, solutions. Solutions are made of a solvent and a solute. The solvent is the thing that dissolves the solute, and is talked about beginning on page 530 in the 10th edition of your textbook. The different kinds of solutions are outlined for you on page 530 in table 13.1, and I'm just going to zoom in on that here for you for a second. You can see that solutions are not necessarily just a water and something, but they can be a gas and a gas stuck together. An example is air. Air is a solution. Liquid and a solid, like salt and water, that's a type of solution too. That's really a popular one. But you can see that you can also have solid and liquid mixed together, or a solid and a solid mixed together to make a solution. Solutions are homogeneous mixtures, meaning that they're the same throughout. You can see that in making a solution, there's an energy change in the process. The energy change in the process is called the enthalpy change. This is delta H. And since it's the enthalpy change in the formation of a solution, your textbook usually puts SOLN down below the delta H. This means that it is the change, that's what triangle means, in enthalpy or heat at constant pressure for the formation of a solution. There are 3 different portions in the formation of a solution. First of all, step number 1, delta H1, is the separation of the solute. This is generally an endothermic process. You have to put energy in. Step number 2, also an endothermic process where you have to separate the solvent. And then step number 3, generally a negative process, is where the 2 solute and solvent interact and give off energy. Remember, enthalpy of any type is always from the system's viewpoint. And the system in this case is the particles that make up the solution. A good example of this is, first of all, on page number 530, and I'm going to zoom in on this just a second. You can see that in this solution process right here, we have sodium chloride surrounded by water. The separation of the water molecules is the first step in the process, which takes energy to be put in. The second is the solvation of the sodiums and the chlorines. You can see that they're being surrounded by the water molecules. So this is being separated. That takes energy to separate it. And then the third part is the new attractive forces between the chlorines and the positive end of the water molecules where the hydrogens are, and the attraction between the sodiums and the negative ends of the water molecules where the oxygens are. These 3 processes, delta H1, delta H2, and delta H3, are outlined for you on page 531 of the textbook. You can see delta H1 right here for the separation of the solute, delta H2 for the separation of the solvent, and delta H3 for the formation of the solute-solvent interactions. And this one is negative. Generally, we can say that the formation of a solute-solvent process is negative, and therefore it happens by itself. It's what's called spontaneous. Spontaneous things generally happen by themselves without outside intervention. Solutions that form with outside intervention, you know, when you just mix 2 things together and you stir them a little bit, are called spontaneously forming solutions. These generally happen when the enthalpy of the solution is negative. But this is not always true. There must be something else going on in here. The something else that's going on in here is something called entropy. Entropy is different from enthalpy. Entropy is the mixed up or disorderness, or the mixed upness, or the random dispersal into space of the molecules of the particles. This entropy or mixed upness is natural. Generally, things tend towards disorganization. And this helps with the spontaneous formation of solutions, especially if their delta H of solution would happen to be positive and be a endothermic process. you should know the term entropy, and we'll actually quantify entropy in Chapter 19 quite a bit more. But right now you should understand that this is also one of the driving forces in making the spontaneous formation of solutions. Three terms identify the solubility of a solute in a solvent. First of all, saturated solutions are one where there is as much solute as possible dissolved in the solvent. Unsaturated solutions are solutions that can have more solute dissolved in the solvent, and supersaturated solutions are ones that have too much solute dissolved in the solvent and yet still remain dissolved. You can actually see an example of these three things on page 536 of your textbook, where it talks just briefly about saturated, unsaturated, and supersaturated solutions. And they have a nice picture down here of a supersaturated sodium acetate solution. They add a seed crystal to it, and you can see a lot of the sodium acetate turn into a solid, and then it goes back to its normal saturated state right here. The liquid portion is saturated. There are four factors that affect the solubility of substances. Factor number one is that like dissolves like. Things that are polar dissolve things that are polar. Things that are nonpolar dissolve things that are nonpolar. Things that are polar and polar that dissolve are said to be miscible. Things that are nonpolar and nonpolar that dissolve are also said to be miscible. Things that are opposites that don't mix, like a polar and a nonpolar thing, are said to be immiscible. They don't dissolve in each other. Like dissolves like is really well illustrated by taking two polar substances of like size and dissolving them. For example, here's water that is obviously very polar and a bent structure, attracting to, this is methanol or methyl alcohol. You can see the OH right here allows it to have hydrogen bonding with a very negative pole right here and a positive pole here. This negative pole attached to the positive pole of the water. They attract and therefore they dissolve, and they're what's called miscible. So step number one in deciding whether something will dissolve is like dissolves like. Second is the size of molecules. Similar sized molecules are easier to dissolve in one another. Not only does oil not dissolve in water because they're different polarities, oil is a nonpolar substance and water is a polar substance, but because they're different sized molecules. Oils are usually really large, long chain molecules, and water, of course, only has a molar mass of like 18 and is made up of 3 atoms. The third thing that decides on the dissolving something, or it affects the solubility of something, is the pressure. The pressure. And this is especially true when you have a solute that is a gas and a solvent that is a liquid. This is governed by something called Henry's Law on page 541. What this says is the solubility of gas in a substance is directly proportional to the pressure above the gas in the container. There's a nice picture of this, an example you see in everyday life, on page 541 of the 10th edition of the textbook. You can see that solubility decreases as the pressure decreases. What they do is they take carbon dioxide and shove it into this bubbling, sparkling mineral water, or soda pop, if that's what it is. And then when you open the top, of course, you release this gas pressure that's above the top of the liquid held in by the cap. When you do that, the CO2 bubbles out of the carbonated beverage. Fourth thing that determines solubility is temperature. Usually for solids, if you increase the temperature of the solvent, you increase the solubility of the solute. This is a graph on page 543. It's the opposite for gases, though. If you increase the temperature of gas, generally the solubility of the gas goes down. Two great graphs for you right here that I want to zoom in on because there's lots of graph questions that show up in this chapter. This is the solubility of solids inside of water at various temperatures. And you can see that you need to be really, really careful when you look at these graphs and look at the units and what is on each axis. Look at that first before you try to answer some kind of question about it. Notice this is the solubility in grams of salt in 100 grams of water. So you're assuming you have a tank or container of 100 grams of water, and you're going to dissolve a certain amount in it at a particular temperature. For example, they could say how much KNO3 dissolves at 40 degrees Celsius. Find 40 degrees, plop up here. This line is the solubility curve line. And you'll notice it's pretty darn close to about 60. Pretty close to 60. It's a little bit off. It's about 58 or I don't know, something about 60 approximately when it hits 40. maybe it's 62 or something like that. Follow that over and you can see it's about 62 grams that dissolve. Now notice that's how many grams of KNO3 that dissolve in 100 grams of water. Trick question they could ask you is how many grams of KNO3 dissolve in 200 grams of water? Well, if 62 or 63 grams dissolve at 40 degrees Celsius in 100 grams of water, double that would dissolve in 200 grams of water, right? So it'd be about like 124 or something like that grams dissolve in that. That's a temperature solubility graph. Lots of questions about those. Here's a temperature solubility graph for gases. And you can see that the solubility of various gases decreases as the temperature increases. This is very common for gases. You can see that in solids, almost all of them increase with temperature, except for this one right here. The cerium sulfate actually decreases, which is kind of unusual. You don't see that too often. Those are the 4 factors that affect the solubility of various substances: temperature, pressure, size of molecules, and then like dissolves like, or polarity. Next in the chapter, we talk about ways of expressing concentration. Mass percent is one of those. Mole fraction is another type of way to express concentration. Molarity is another method of expressing concentration or amount of solute dissolved in total liters of solution. Watch out for molarity though, because this will vary with temperature, and when the solute dissolves, of course, you can change the volume of the solution. It varies with temperature because the volume of the solution will vary with temperature as well, because it will expand or contract depending on what the temperature is. And so the last one is molality. Molality is moles of solute divided by kilograms of solvent. This is immune to temperature change because, of course, the mass of the solvent is not going to change unless some of it evaporates. Page 545 and 546 in the 10th edition give you tons of example problems for these types. And if you want to see me actually do some, you can look back in the video cast and look in the video cast like 4 and 5 or so from this chapter, and you'll see me do a bunch of these types of practice problems right here where they give you molarity or molality and ask you to convert between the two. And then here's one with mole fraction and molality as well, where you can convert between those two. You can take a look at these sample exercises, try the practice exercise, see how you do. You can take a look back and watch me do some of those as well. Here's the calculation of molarity when you're given a certain amount of grams of solute and solvent, and they give you a density of the solution as well. You can see this little chart and diagram and interconverting between those, and you should know how to do that. Lastly, in this chapter, it talks about things called colligative properties. Colligative properties are properties that depend on the amount, not the nature of a solute. Nature meaning whether it's some type of salt or whether it's sugar or whatever it is. It doesn't matter what it is as long as there is a certain amount of it. It depends on how much, not what, is dissolved in a solvent. Depends on how much, not what, is dissolved in a solvent. There's 4 colligative properties: vapor pressure lowering, boiling point elevation, freezing point depression, and osmosis. We're going to take a look at each one of these in the textbook, and I'm going to talk about them just a little bit. And then I'll do a few sample exercises with them and actually give you some idea of what they're like. But most of it actually was done on previous video casts, and you can try some of those calculations yourself. Lastly, there's some molar mass calculations on page 556. And some people forgot in this chapter what the word molar means. Molar, of course, means per mole, and that's grams per mole. It's known as molar mass, molecular mass, and there's some calculations for that on page 556. So let's take a look at each one of the colligative properties really quick. The first one is called vapor pressure lowering. Vapor pressure lowering. Vapor pressure lowering means that if you have a solute and a solvent mixed together, you take the vapor pressure of the solvent and you make it less than what it normally is. Now, let's back up. Some people don't remember what the words vapor pressure mean. This means that something evaporates from the liquid to the gaseous state, and that gaseous state causes pressure inside of its container. So, for example, right here, looking at these little diagrams, here's a pure solvent. This pure solvent, they actually show some gaseous particles that have evaporated from the surface and are bouncing off the inside of this container, causing some pressure inside of this container. Now, when you dissolve a solute in the solvent, these little particles are less in number because some of the solute and the solvent actually bond together, and less of it evaporates. Less of it evaporates because the vapor pressure is lowered due to this solute-solvent interaction. Now, solute-solvent interactions can be calculated as to how much they change the vapor pressure by using something called Raoult's law. Raoult's law is to ideal solutions like ideal gases are to the ideal gas equation. Raoult's law says that the pressure of a solution, the vapor pressure of a solution, is equal to the mole fraction of that solvent multiplied by the original vapor pressure of that solvent. So this is the pressure of the solution multiplied by, and then this is the mole fraction of the solvent multiplied by the vapor pressure original. That's what this little O means, of the solvent right here. You can see an example problem right down below here where you notice the vapor pressure is in a unit of pressure, torrs in this case. And you can see it was actually lowered from 17.5 to 14 because the part of the solution that is now water, or the solvent, is only 0.8 as far as mole fraction is concerned. So the vapor pressure of something can be lowered by adding a solute to a solvent. Let's go through two other terms that they use right here. And these are volatile and non-volatile. Some people forgot what these terms mean from chapter 10 too. Volatile means that it has volatility to it. It will evaporate and go from a liquid to a gaseous state on the surface fairly easily. A non-volatile substance is one that doesn't evaporate or doesn't change from a liquid to a gaseous state very much. You, of course, couldn't calculate the vapor pressure of something that is completely non-volatile because it wouldn't have a vapor pressure at all, because it wouldn't turn into a gas at all. If something is too volatile and evaporates immediately and doesn't remain in the liquid state at all, that'd be tough to say that that's a very good solution to check to apply Raoult's law to as well, because it's not really a solution or a liquid. It turns into a gas right away. To apply Raoult's law, what you need to have is what's called an ideal solution. And an ideal solution is one that has like size and like polarity. Like size and like polarity. If things don't have like size and like polarity, they don't obey Raoult's law very well. Kind of like things that aren't gases don't obey the ideal gas law very well. The next two parts are boiling point elevation and freezing point depression. These are two more colligative properties that depend on the amount, not the nature, of the substances that are dissolved in them. You can look at this phase diagram to explain both boiling point elevation and freezing point depression. You can see right here in this phase diagram, here's the solid, here's the liquid, here's the gaseous area. And this black line here and this black line here differentiate or show where the freezing point between liquid and solid is and the boiling point between the liquid and gas is. When you add a solute to a solvent, in effect what you do is you change this liquid-solid barrier and move it more towards the solid. You change this liquid-gas barrier and move it more towards the gaseous phase. And so you can see that you actually increase right here. You increase this area or space between where the substance is a liquid. It used to end right here and right here. You used to go from liquid to solid or from liquid to gas right here. But now you've increased the time in which it spends in the liquid phase. You've elevated the boiling point. You can see delta TB. You've lowered the freezing point, the delta TF right here. You can calculate boiling point elevation and freezing point lowerings, and there are a number of sample calculations on page number 552 in your textbook, and I encourage you to take a look at them. Work them through. Work them through on your own and then look back to see how they did them. Look back at the video cast from before and see how I worked them. You should know how to apply these molal, freezing point, and boiling point depression constants and understand how delta T is equal to K times M for boiling and freezing. The last type of colligative property is called osmosis. Osmosis is talked about on page 553 of the 10th edition. And osmosis is the net movement of solvent toward the solution with a higher solute concentration. And this diagram right here actually explains it extremely well on page 554. You can see that we have a more concentrated solution here, separated by a semi-permeable membrane, and then we have a less concentrated solution over here. The less concentrated solution wants to go and dilute the concentrated solution, so then they can be equal. This difference in pressure that actually develops is symbolized by the Greek letter pi, and it's called the osmotic pressure. And you can see how the net movement of solvent is greater than the to dilute the substance is greater than any other movement in the little U tube right here. You can see the calculation for finding osmotic pressure right here, where pi is equal to mRT, and you can see that pi, osmotic pressure, is directly proportional to the molarity of the system. Last section in the textbook talks about colloids. Colloids, of course, are dispersions or suspensions of particles throughout water. They eventually settle out because of gravity, but these dispersed particles are much larger than water molecules, and therefore they just float around and actually can cause what's called the Tyndall Effect. You can see that there are a number of different types of colloids down here. Some of them that are interesting are things like fog, smoke, whipped cream, paint, marshmallows, all those types of things, and you can see some beautiful pictures over here of what are called the Tyndall Effect as light goes through a colloidal suspension. A couple other of colloids over here in things that are living systems as well. Let's talk about one more thing with colligative properties, and this shows up as a test question quite often. In boiling point elevation and freezing point depression, the equation is generally delta T is equal to I times K, either freezing or boiling, times the molality. I times Kf times freezing times the molality. The molality is, of course, moles per kilogram of solvent. K is the freezing point or boiling point depression constant. And delta T is the change in freezing or boiling point. I stands for what's called the Vant Hoff factor. And this tells you the number of particles per formula unit dissolved in the solution. So, for example, if you have KCl and you dissolve that, an ionic compound, you get K plus and Cl minus. Notice you get 2 particles per formula unit, and 2 would go in here for the I. If you take something like sugar, C6H12O6, and it's totally molecular, non-ionic, you just get this 1 particle dissolving, and so I would be 1. I would be 1 because 1 thing dissolved in it. Take something, for example, like Ca3P2. This would dissociate, and it would form 3 calciums and 2 phosphides. 3 plus 2 is 5, and so you'd have 5 for the I right here. Now, the Van Hoff factor is actually talked about in great detail in your textbook on page 557. And I encourage you to take a look at that if you're interested in it, because it talks about how there's ion pairing, and this number never is exactly 5. In this case, it's never exactly 1, and it's never exactly 2 right here. But it comes close. And you can generally tell which thing is going to cause more of a freezing point depression or a boiling point elevation, looking at how many particles you get per formula unit for the substance. Find your test. The next portion is to go through and make corrections on all of the problems that you got incorrect in Chapter 13. So this is the correction of the Chapter 13 multiple choice individual test. Make sure you have this actual test done in front of you. Make sure that you have a piece of paper where you can do your corrections. To do your corrections, you're required to do 3 things. Number 1, you're supposed to write down the problem number and the correct answer. This is for each problem that you get wrong. Number 2, you go through and you write down why you got the problem wrong. What did you do wrong that you now know that you shouldn't do again? And it can't just be, I didn't know something. It has to be, oh, I didn't understand that colligative property. I didn't understand that boiling point is elevated and freezing point is depressed. It has to be something like that. And number 3, you have to give a reason why you will not get it wrong, get a problem like this. Well, not get a problem like this wrong again. Okay? You have to do that for each one that you get wrong, and I'm going to go through, I'm going to model it for the first one, and then I'll model it for a few other ones along the way. So, have this out, have a piece of paper out in front of you, and you can skip ahead to the problems you got wrong, but you can't skip any that you got wrong. You got to staple this to your test along with your Scantron sheet to earn the options available to you in the future. Problem number 1. Use the following answers to complete the first 3 questions. Number 1 says, is not a colligative property. Well, there are 4 colligative properties. Remember, boiling point elevation, vapor pressure lowering, freezing point depression, and osmotic pressure deviation, or osmotic pressure. And so B, surface tension degradation, there really is just the breaking down of surface tension, is not a colligative property. It doesn't depend on the amount of substances that you have. So 1B, why did I get it wrong then? I got it wrong because I did not know the 4 colligative properties. This actually was one of the easier questions on the test because all it was a recall question. And if you don't know those, well, you're going to struggle. Then why am I not going to get it wrong again? Because I memorized the 4 colligative properties. All right, I know what they are, and I can recall them once they're given in a list. Number 2, occurs across a semi-permeable membrane. Well, this is called, I should put the answers down here. B for number 1. 2, the answer is E, osmotic pressure occurs across a semi-permeable membrane. And then number 3 can be calculated using Raoult's law. Well, this is vapor pressure lowering. That's what you use Raoult's law for, is vapor pressure lowering. Number 4, a sample of H3BO3, which is boric acid, is dissolved in 1,000 grams of water. To make a 1 molal solution, which the following best procedure to determine the molarity. Remember, molarity is equal to moles divided by liters of solution, total liters of solution. This is moles of solute. Shouldn't be too hard to get the moles of solute because I'm given the grams of solute and the formula, so I can look on the periodic table and I can convert to moles. The thing that I don't know, I know the grams of water, but I don't know the total volume of the solution after I've divided this, dissolved this 61.8 grams into the 1,000 grams of water. And so the thing that I want to know is I want the total volume of the solution right here. That's going to help me find that. Number 5, the answer is D as in dog. The volume of distilled water that should be added to 10 milliliters of 6 molar HCl in order to prepare a 0.5 molar solution. So this is most easily told you by using the dilution equation. This is a review problem actually, where the molarity original is 6 molar, the volume original is 10 milliliters, the molarity final is 0.5 molar, and the final volume is unknown. So I divide both sides by 0.5 or 1/2. 60 times 1/2 times 2 is 120. So that's equal to my volume number 2. That's my total volume at the end. But be careful, it says how much water should be added. And we're starting with 10 milliliters, so 120 minus 10 is 110 milliliters. Tricky problem. Number 6, solution formation between a liquid solute and a liquid solvent is favored by number 6. The answer is B as in Bob, a decrease in enthalpy and an increase in entropy. We talked about that in the notes, that enthalpy would have a negative value generally, and then entropy would be a positive value because you'd want more disorder or disarrangement, and a decrease would be negative. Number 7, predict which pure liquids will be miscible in solution. That means that they can dissolve together in solution. Remember, like dissolves like in this case. And number 7, the answer is B as in Bob. which is 1 and 2. Carbon tetrachloride and heptane are both nonpolar solvents, and then water and propanol both have hydrogen bonding in similar size. Notice acetone and octane, one has a polar molecule right here, one's nonpolar, and they're not quite the similar size enough to be soluble as well. Next page, number 8. The next 3 questions actually use this diagram right here, and being able to read the graph is critical to being able to do these types of problems. Number 8 is B is in Bob. It's got 100 grams of water and 91 grams of KNO3, and it's heated to 60 and thoroughly stirred. When the system's cooled from 60 to 20, a white crystalline solid forms. What best describes this liquid phase of the system? So we were at 60 degrees right here, and we had 91 grams of the salt in there, 91 grams of KNO3, so we're way up here, 91 grams right here. Okay, then it says it's thoroughly stirred until when the system is cooled from 60 to 20, so now I'm going from 60 to 20 right here. 20 degrees is right, it would be right up here. So I'm going from here to here. Notice how I crossed the solubility line here for KNO3. At 20 degrees, I'd actually cross the KNO3 line right here, where I could have about 30 grams of salt dissolved. Okay, that would be the saturation line right here. Okay, saturation line. And so 30 grams of KNO3 would remain dissolved, whereas the other 61 grams would sit in the bottom of the bucket. So I would have 30 grams of KNO3 dissolved in the 100 grams of H2O. And I remember it says right here the liquid phase of the system, so I'd have 130 grams total of solution, with 30 grams being the KNO3 in there. Notice how it dropped down here, and I got to this line right here because that's how much can dissolve. That's the solubility line right there. Number 9, the answer is C as in cat. You can find the resulting solution by looking up here and finding out that it's a saturated solution because it's right on the line after you follow those. And number 10, the answer is B as in Bob. And you can see that it's a saturated solution and that there's 20 grams of KClO3 dissolved in the solution when it's saturated at that temperature. Reading the graph, folks, take a look at it. If you're struggling with the graph reading, take a look. Make sure you're looking at the units over here on the side and the temperature down here and following up to the solubility line. Moving on to number 11, the answer is E as in egg. Saturated solution of KNO3 in equilibrium at extra prior to 20 degrees Celsius, which describes the solution temperature after increase to 40 was still in the excess contact with solute. The answer is E, 1, 2, and 3. The molality of the solution increases, the solution remains saturated, and the density of the solution increases. Because notice you went to 40 degrees Celsius, so you allowed more of the solute to dissolve. And remember, molality is equal to moles divided by kilograms of solvent. You didn't change the amount of solvent, but you changed the number of moles of the stuff that are dissolved in there. The density of the solution also went up because you dissolved more of this moles of stuff in here, so now you have more grams of that stuff dissolved per milliliter of the solution, because that's what density is. Remember, density is equal to grams per milliliters, or density is equal to mass per unit volume. Number 12, the answer is E as in egg. 13 is E2, just so I'm ahead of the curve here. When pure water is compared to an aqueous salt solution, the pure water will have a lower boiling point, a higher freezing point, and a higher vapor pressure. Remember that when you dissolve a solute in a solvent, you lower the vapor pressure, you cause that solution to have a lower freezing point or have a freezing point depression, and you also cause a boiling point elevation. So notice it says the pure water right here, so that fits all those descriptions. Number 13, a solution contains equal masses of glucose and propanol. What is the mole fraction of propanol in the solution? So it says equal masses. So what I recommend when you do something like this is just, pick a number. And so you can say a mass of glucose is, 1, And well, what's easy is if you pick the molar mass. So if you pick 180 grams of glucose, and then of course it says equal masses, so 180 grams of propanol, and then take those and convert them to moles. And I chose these numbers because that's their approximate molar mass. So 180 grams in 1 mole, 180 divided by 180 means there's 1 mole of the glucose. And then this has a molar mass of 60 grams in 1 mole, and 180 divided by 60 is pretty easy. That's 3, right? So there's 3 moles of the propanol. And now it says, what is the mole fraction of propanol? Well, propanol would be the mole fraction, remember, is part divided by whole, and the part that's propanol is 3, and the part that is the whole thing is 3 plus 1 or 4, so 3/4 would be the mole fraction. That would be propanol, and that's E. None of these because 3/4 isn't given there anywhere. Number 14 is C as in cat. When benzene and toluene are mixed together, they form an ideal solution. If benzene has a higher vapor pressure than toluene, then the vapor pressure of a solution that contains an equal number of moles of benzene and toluene will be lower than the vapor pressure of benzene, higher than the vapor pressure of toluene, because you want to hit in the middle. You want to hit in the middle. So benzene had the higher vapor pressure, toluene had the lower vapor pressure. So we form an ideal solution. We kind of meet in the middle because their vapor pressures would be a mixture of the two. Which has the highest boiling point? This is a good question. This is number 15. The answer is D as in dog. So what you want now, since they're all the same molality, is you want to look at how many particles you get per formula unit. In NaCl, you'll get 2 particles because you get Na plus and Cl minus. In KBr, you get 2 particles. In CACL, you'll get 3 particles. In K3PO4, in K3PO3, you'd get 4 particles, and in Mg, because 3K plus is in PO3, and in MgNO3 you'd get 3 particles. So the one that gives you the most particles is D as in dog right here. Because remember, the freezing point or boiling point, delta T, is equal to I times K boiling times the molality. Well, the molalities are all the same. The K is all the same because you're assuming this is the same well, it's molality, so it's in a water solution. So you just look to the I right here, and the bigger I, the bigger the boiling point or change. When water cascades over waterfall, more oxygen is dissolved in water, which factor will also contribute to an increase in oxygen gas dissolved in water. Number 16 is C as in cat, decreasing the temperature. Lower temperature, more gas dissolves. Number 17, sulfuric acid and water become noticeably warmer when mixed. This is due to number 17. The answer is E as in egg. The strong attractive forces between the solvent in solute in the solution than in pure liquids. Remember, that's the third portion of solution formation, is that the solute and the solvent interact. Number 18, which is expected to be most soluble in hexane. Well, hexane, remember, would be hex, C6, and then H2N plus 2, H14. It's a long chain hydrocarbon that's totally non-polar, and there's no hydrogen bonding or anything like that in there. And the answer is 18C as in cat, which would be C6H6, another non-polar hydrocarbon. Number 19, what is the percent methanol by mass in the solution? Contains 40 grams of methanol and 60 grams in water. And notice it's percent by mass, so it's mass percent of methanol in water. So it'd be part divided by whole. And the answer to this is C as in cat. The part that's methanol is 40. The whole thing together is 40 plus 60, or 100. And then you multiply that by 100%, so it's 40%. Next 2 questions refer to the solubility curve. In number 20, the answer is D as in dog. You get an unsaturated solution because you're below this line right here when you follow along the 40 grams and 60 degrees. In 21, the answer is E as in egg, which means there's 135 grams in solution, including 35 grams of solute when you get to that point. Another one of those, just like reading the graph before, except for this is just a different little shaped graph. Number 22, which accounts for the Tyndall effect in colloids. This is A as in aardvark, the scattering of light by particles of matter. Number 23, which applies to a 2-molar solution of sodium nitrate in water. The answer to this one is E as in egg. This is parts 1, 2, and 3. Adding water raises the freezing point. Remember, the freezing point is depressed when it's more concentrated. This would make it less concentrated. Adding water increases the vapor pressure of the solution. That's true because remember, there's vapor pressure lowering. And then number 3, adding water decreases the density of the solution, which is true because you have less solute in there per volume of solvent, because density is equal to mass divided by volume. You're increasing the volume, and of course you're decreasing the mass because the solute right here weighs more than just the pure water solvent that's in there. 24, the answer is E as in egg. If the temperature of an aqueous solution in alcohol is increased from 20 to 90, assuming no change in the mass of the solvent, which the following statements is true, the mole fraction of the solute increases. Number 25, the answer is D as in dog. Which of the following pairs of liquids forms a solution that's most ideal? Most closely follows Raoult's law. Where Raoult's law, remember, is for ideal solutions. And ideal solutions are one where the like dissolves like. So you want to find ones that are together, that are polar and polar, or in similar size, or ones that are nonpolar and nonpolar, that are similar in size. And C6H14 and C8H18 are pretty close in size, but they're definitely both nonpolar as well. Number 26, the answer is C as in cat. Why are alcohols more soluble in water than straight-chain alkane molecules such as pentane? Well, alcohols, remember, contain the COH bond in there. This OH bond is hydrogen bonding, and this hydrogen bonding thing right here can bond with water molecules. You should know that, and if you didn't know this, this is a good chance to learn this, that alcohols have an OH attached to the end of the chain or somewhere in the chain that causes it to have hydrogen bonding characteristics. Number 27, a solution is made by dissolving a non-volatile solute in a pure solvent. Compared to the solvent, the solution, number 27, will A, have a higher normal boiling point. Its boiling point is elevated because you dissolved something in it. It doesn't matter what the solute is as long as you dissolved something in there. And then number 28, sodium chloride is least soluble in which liquid? That would be B as in Bob, carbon tetrachloride, because it is nonpolar and therefore it can't dissolve things that have dipoles like Na plus and Cl minus that have a positive and a negative ion in there. That's a test. Make sure that you write it up with a correct answer for each one, why you got it wrong, and it's got to be a real reason, and a reason why you will not get a problem like this wrong again for each one. Pause the video, rewind it, make sure you got each one of them done. Then you're eligible for some new things. Thanks for joining us for the explanation of the Colligative Properties Chapter 13 test.